All right, we're going to look at our last derivative rule for now, and that's the chain rule. And so what the chain rule is it allows us to take the derivative of functions that are within other functions, right? So a little composition of functions here. What I can do for these types of functions is I can take the derivative of the outer function and leave its input alone, right? So leave g of x alone. And then I can multiply by the derivative of that inside of that composed function after the fact, right? So g of x is not going to change at all inside these brackets. I'm just taking the derivative of the outer function, and then I can take the derivative of the inner function. A lot of these times, these outer functions will see exponents on binomials, trinomials. We're going to do this a lot with radicals. We can do this with sinusoidal functions. Anytime where the input of the function can be a function itself. And it allows us to kind of simplify things rather than expanding out to separate terms or anything like that. So we have f of x equals the square root of 3x squared minus x plus 1. So when I think about this as a function inside a function, I could say I have some square root function and then some quadratic function. Right? And the quadratic function is the input in that basic square root function. Right? So when I'm thinking about which function to do first, well, I'm going to do the square root, and then I'll deal with its insides. It can also be helpful to write these things as a power, because then that allows me to more easily apply that power rule. So f of x here is this whole quadratic 3x squared minus x plus 1, all to the power of 1/2. I'm going to do that power of 1/2 first. So I'm going to take the derivative of h of x first, right, which is just using the power rule here. So I bring that power down. So f prime of x, let me make some more space. F prime of x is 1/2 3x squared, and I'm leaving the whole inside alone, right, the whole inside function to the negative 1/2. Times, and now I'm going to take the derivative of that inside function. So now I'm going to say 6x minus 1, right? Because the derivative of h of x, let me make some more room here. The derivative of just the square root of x, h prime of x, is 1/2 x to the negative 1/2. So I did that, right? But instead of x, I had function g. And so if g of x was 3x squared minus x plus 1, the derivative of g is just using that power rule and the the sum difference rule, 6x minus 1. So I can leave it like that. I could rewrite that exponent if I want, right? Remember with those negative powers, with those radicals, I have a denominator of 2. And then I have a 3x squared minus x plus 1 in a square root in the denominator now because of that negative 1/2. And I have a 6x minus 1 as the product on top. So doing the same thing again. Right, let's do this first, my outer function first, and then this, my inner function, my composed function second. So when I take the derivative, f prime of x, I just apply that power rule as if I had x to the power of 3. I leave my insides the same. I drop the power by 1. Then I multiply by the derivative of the insides there, right? So this is the derivative of x squared plus 1. This is the derivative of something cubed. Right, and then I'm not super concerned about that simplification right now. We'll talk about when it's helpful to simplify and when it's not. But if I really wanted to call this 6x, making sure you know where your powers are, what you can combine, what you can't using that order of operations, but the 3 and the 2x are just products. So there's f prime of x. G prime, same idea. Drop the power, leave the insides all exactly the same. Then the product is the result of the derivative of the inside, 3 minus 4x. Make sure you put brackets. The brackets are essential here. Otherwise, you are writing improper notation and you're only multiplying by the 3. So be careful with that. And again, I could distribute this. I could choose not to distribute this. It does not matter at this point. When I have you guys write your assessment, I won't bother with the simplification unless we're actually using it to apply, right, applications or something. So let's do another one. Again, this time it might be helpful to write anything. If I can avoid the quotient rule because it's long and messy, I'll try to, especially with that numerator being just a constant. So this is the same thing as a -7, and then a 2t minus 3 to the -2 as a product, right? And then I don't need to worry about product rule because of that coefficient out front is just a number. If there was an x here though, right, in this section here, oops, if there was an x, then I'd definitely have to be doing product rule. So I take the derivative. I can pull that coefficient out front, and then I can just deal with the derivative of the rest of this. So -2, leave the insides the same, drop the power by 1 to be a -3, then multiply by the derivative of that inside function there. And again, this is the result of taking that power rule, that outer function. This is the result of taking the derivative of that inner function. And because this one's easy to clean up, we'll just show you that you can do that, right? It's all products. It's kind of nice here. I'm doing the -7 times the -2 times the +2. That's going to be my whole numerator. So 28. And then I just have a 2t minus 3 cubed in my denominator. All right, let's try a couple more. All right, so here in this first one, I'm going to have to use product rule this time, and then I'll have to use chain rule. All right, so I'm looking here, I have function 1, I have function 2, which is the square root, and then this function 3 that's composed inside of there. So what I'm going to have to do, right, is do that normal product rule, but when I do the product rule of the second part, right, so if I have f of x times g of x, let's just do this. If I have f times g, the derivative looks like f prime g plus fg prime, but then beyond there, the g prime is the whole g prime h times h prime, right? All of those functions, I have to make sure I'm doing the right order of those rules. So the derivative here is going to be, I do 2x, and then I leave this whole thing alone, right? Because that's leaving, right? When I do function f prime, here it is. Oops, I lost my equal sign. When I do leave function g alone, here it is. Now, when I take the derivative is where that chain rule applies, because chain rule doesn't apply until I take the derivative of a composed function. So now I do an x squared. Now I will do 1/2 1 minus x squared to the -1/2. And now I do a minus 2x. Right, so all those little bits and pieces. This is the derivative of the inside. This is the derivative of that square root function. And I still left function f alone for the second part of that product rule, right? Quick simplification of that leaves me with a 2x root 1 minus x squared. Keep in mind that you have that addition sign now, so be careful. They're not all products. And then I have plus, I'll call it a negative actually, minus 2x cubed over 2 square root 1 minus x squared from that negative power of 1/2, right? And then these would cancel as well. All right, let's try it with some quotient rule now, right? And again, quotient rule can almost always be done as, well, it can always be done as just product rule with a negative power, but let's go through the process of doing quotient rule because why not? So it's going to be f prime g minus fg prime over g squared. This is the only case where that composition, that chain rule, has to apply, right? Otherwise, everything is kosher. Nothing else is a function inside a function. So let's go ahead. F prime of x is, derivative of x is 1. Don't have to include it, but you can. X squared plus 4 minus, now it's x. Now it's the derivative of this thing, right? So when I take the derivative of this denominator portion, so when I do dx of x squared plus 4 to the 1/3, I'm getting 1/3 x squared plus 4 to the negative 2/3 times 2x from that derivative of the inside. Right? So I get 1/3 x squared plus 4 to the negative 2/3 times 2x. And all of that is still just in that second term of my numerator using quotient rule. And then in my denominator, I just square it. And again, square can go inside the radical, square can go outside of the radical. It's the same thing as a 2/3. It would have the same denominator, the same radical as this thing. And I'm going to leave that one. If you want to take the adventure to simplify that, go right ahead. All right, g of x. So now I have quotient rule inside, right? So if I have g prime of x, at some point I'm going to be taking the derivative of just that fraction. Oops, 3x minus 1 over x squared plus 3, right? Which is going to use the whole quotient rule. And so when I take g prime of x, I use that power rule. I keep the insides exactly the same. So 3x minus 1, x squared plus 3. None of that is going to change, right? Power of 1, until I do my whole quotient rule here. So derivative of the first thing, leave the second thing alone. 3x minus 1, give myself a little more room, times 2x, right? Again, derivative of the top is right here. Derivative of the bottom is right here. All of that divided by x squared plus 3 squared. So in this case, g prime of x, because it's just all multiplication, I can simplify that one a little bit. I'm not going to go too far with this, but I have a 2, I have a 3x minus 1. All of that is times this whole numerator, which is a 3, x squared plus 3 minus 2x, 3x minus 1. And then all of that is over x squared plus 3 cubed, because I had 3 of them, right? 1 here, 2 here. But not worth expanding unless, as we'll talk about in a little bit, if I wanted to continue to take the derivative, right? If I want to take another derivative of this function, it's a lot easier to start from something that's simplified, because then there's less of that chain rule, less of that product rule involved, and more of just my good old sum difference rules. All right, last one, p prime of t. I'm going to use product rule again here. So first derivative, 10, leave the insides alone, drop that by 1, multiply by 2, right? That's the whole first derivative done. Now I leave the second thing alone, right? That's my f prime g, basically. If I called this f of x and I called this g of x, maybe I'll write that off to the side here, f prime g. Then to that I'm going to add, and then I'm going to do g prime f, or fg prime. Right, so leave the whole first thing alone, 2t minus 1 to the 10 times. Now do that whole, t minus 1 squared. Now multiply by the derivative of the inside, which in this case is just 1. All right, and this whole thing is my f times g prime. All right, so beyond there's a bunch of application problems for you. Because we spent the last few days going through some of these application problems, I'll get you to go ahead and give these a try. It's going to be the same process as before, right? All we know how to do so far is that, hey, I can find my tangent slope by taking the derivative, and I can also find my normal slope by taking 1 over negative 1 over my tangent slope, right? They're perpendicular to each other. They are negative reciprocals of each other. So give these other few tangent line problems a try and feel satisfied that you learned chain rule.